Hi dears, I welcomes you for the today session about electric charges. What is that one? Electric charges. Let's see what are the outline characteristics of today's session. And today's session is dealing about fractional electricity, properties of charges, Coulomb's law, Coulomb's law in vector form, units of units of charge, relative permittivity or dielectric constant, continuous charge distribution with charge density, linear charge density, surface charge density, and volume charge density. So these are the outline of the today's session. Let's see here what is fractional electricity. Fractional electricity is the electricity produced by rubbing two materials or rubbing two suitable bodies and transfer of electrons from one body to another body. Just you take here what is the concept of the fractional electricity. Fractional electricity is the electricity produced by rubbing of two bodies. The electricity produced by rubbing of two bodies. Let's see here. We are taking two bodies in figure 1 and two bodies in figure 2. In figure 1, this body is a glass and this body is the silk cloth. Glass and silk cloth. In figure 2, ebonite rod and fur. Ebonite rod, fur. So here, taking these two different materials and rubbing together both the bodies of figure 1 and figure 2. Now here the glass is rubbed with the silk cloth and in figure 2 the ebonite rod is rubbed with the fur. Then here what is happening? When these bodies are rubbing together, the glass and silk cloth, what is happening? Here, when the glass and silk cloth both are rubbing together, from the two bodies, the electrons will be displaced. The electrons will be displaced. So here what is happening? Electrons are displacing. You can see here, that means electrons in the glass are loosely bound in it. So you are taking the glass. In a glass the electrons are loosely bonding. In silk cloth the electrons are tightly bonding. In glass, loosely bonding. In glass. In silk cloth, tightly bonding. So what is happening when glass and silk are rubbed together? Glass and silk rubbed together. The loosely bounded electrons from the glass get transferred to the silk. So the electrons from the glass transferred to the silk cloth. Electrons from the glass transferred to the silk glass. So what is happening? That means as a result, the glass becomes positively charged body. That means glass is donating the electrons. Transfer means what? The glass is donating the electrons where the silk cloth is receiving the electrons. That means glass becomes as a positive charged body and silk become as a negatively charged body. In the figure 2, electrons in fur are loosely bound. In figure 2, the electrons in fur are loosely bound and electrons in ebonite are strongly bound. That means tightly bound. More electrons here and they are tightly in for the electrons are loosely bound. So that's why the electrons are loosely bonding in the fur and tightly bonding in the ebonite. Then what is happening? Let's see here. When ebonite and fur are rubbed together, ebonite and fur are rubbed together, what is happening? Loosely bound electrons from far, loosely bound electrons from the far get transferred to the ebonite, so the electrons from the far transferred to the ebonite. As a result, ebonite becomes negatively charged body. Ebonite becomes negatively charged body and fur becomes positively charged body. Fur is a positively charged body. Ebonite is a negatively charged body. That means in the electrification process, what is electrification? Electrification nothing but rubbing of two bodies. When two bodies are rubbing together, from the two bodies the electrons are shifting from one surface to another surface, and this process or this phenomena is called as the electrification. From the process of the electrification, the word electricity is produced. Let's see. Next one is about the next outline is about the properties of charge. Let's see what is meant by charge. First of all, what is meant by charge? Just you take a just we are taking that one a conductor. So as we know that this is the terminal of conductor, and this is also another terminal, and this will be represented by symbol A, and this will be represented by symbol B. And just imagine here the electrons are flows from direction A to point A to point B. Here A and B are the terminal points. A and B are the terminal points. The electrons are flowing from terminal A to terminal B. From A to B, the electrons are flows. So, meanwhile, whenever the electrons are flowing from A to B, we can observe that one. At the terminal points of A and B, we observe that one more number of electrons accommodated, more number of electrons are presented, more electrons are present at the terminals of A and B. At the point A and B, there are more number of electrons are present when compared to this middle cross section area, where A and B are the terminals. In this terminal location, more number of electrons will be presented. How many number of? More number of electrons when compared to this area. So a region which accommodated or which combined or which is associated with the more number of electrons, and that region is called as the charge. What is that one? Charge. So where more number of electrons are present, you are taking this is the material, and this is about the a particular material, and this is the terminal A, and this is the terminal B, and the electrons more are present at the terminal A and B, and more where the electrons are present more, and these areas are called as the charge 1, charge 2. Charge 1 is represented by Q1 and charge 2 is represented by Q2. So here charge means where number of electrons are accommodated, where number of electrons are present, that locations will be called as the charges. Now here our topic is about the properties of the charges. What is that one? Properties of the charges. Let's see. The first property here, there exist only two types of charges, namely positive and negative. As we discussed just now, there are two charges will be present. One is at A, one is at B, and one will be considered as the positive, the another one is called as the negative. There exist only two types of charges, namely positive and negative. Second one, like charges repel and unlike charges attract. What is that one? Like charges repel and unlike charges attract each other. This is about the point 2. That means like charges means what? Q1 will be repel. Q1 and Q2 will be attract. So from the point 1 we can say this is called as the positive charge, and this is about the negative charge. Now positive and negative will be attracted. Positive and negative will be attracted. Then positive charge and positive charge will be repelled. This is about the like charges. This is about the unlike charges. Unlike charges will be attract. Like charges will be repel. Third one, charge is a scalar quantity. What is that one? Charge is a scalar quantity. Charge is a scalar quantity. Then charge is a fourth one. Charge is a additive in nature. That means we can plus. That means what we can do? We can add. You can take this example here. Example 2 coulombs, 3 coulombs minus 3 coulombs. How much? This is 3 plus 2, sorry, 2 plus 5, 7, 7 minus 3, that means 4. This is about the additive character. And property 5, charge is quantized. Let's see what is meant by quantized. Electric charge exists in discrete packets rather than in continuous movement. That means electron charge is stored in or existed in the form of discrete packet. What is meant by discrete? Discrete means what? Closed. Discrete. So electric charge exists in discrete packets rather than continuous form, rather than continuous amount. It can be expressed in integral multiples fundamental electronic charge. That means Q equal to plus or minus Ne. Q equal to plus or minus Ne, where N is a 1, 2, 3 up to so on. E is the charge of electron, which means 1.6 into 10 to the power of minus 19 coulomb. 1.6 into 10 to the power of minus 19 coulombs. Then property 6. Charge is conserved. Let's see what is the meaning of this one. The algebraic sum of positive and negative charges in an isolated system remain constant. What is that one? The algebraic sum of, that means I1 plus, sorry, you are talking of the charges, no? So Q1 plus Q3 plus Q5 is equal to Q2, Q4, Q6, and this is about the algebraic sum, and this will be 0, and this algebraic sum is 0, and this will be called as the remain constant. The algebraic sum of positive and negative charges in isolated system remain constant. That means you can see clearly with the example, when a glass rod is rubbed with silk, negative charges appears on the silk and an equal amount of positive charge appears on the glass rod. The net charge on the glass and silk system remains zero before and after rubbing. Before and after rubbing. You can see the figure 1. So this is only, see, you can see on the glass rod you will be see positive charges. On silk cloth you will be identify negative charges. So this is about the meaning of the this conserved nature. Then the next outline is about the Coulomb's law for force between 2-point electric charges. Force between 2 points, or there is a mistake, 2-point electric charges. You need to consider 2-point space, 2-point electric charges. So Coulomb's law is a relation. It's a law which describes the relation between force and electric charges. Force and electric charges. Let's see here. The electrostatic force of interaction between 2 points electric charge is directly proportional to the product of charges and also proportional to the square of the distance between them and acts along the line joining the two charges. So that means what? Here the Coulomb is introducing a particular law to find out the relation between force and charges with their spacing distance. So, according to his law, we can analyze that the force which acting on the two bodies is proportional to product of charge 1 and charge 2. Product of charge 1 and charge 2. The force is proportional to Q1 and Q2. Similarly, the force is inversely proportional to 1 by r square. Inversely proportional to 1 by r square. So just imagine this is the force. The force is activating on Q1. The force is activating on Q2. This is in the proportionality manner. Let's you take r, the force is working inversely proportional to their distance. So that's why we taken 1 by r square. That means when you're taking the first equation, if the product of q1 and q2 increasing, the f also will be increasing. And the case 2, that is, if r is decreasing, f will be increasing. R is decreasing, f will be increasing. This is opposite manner in case 2. In case 1, that is same manner. So here f is proportional to q1 and q2. F is inversely proportional to 1 by r square. By clubbing these two equations, by combining these two equations, we will get f is proportional to the q1 q2 by r square. Then remove the proportionality. Then we get f equal to k into q1 q2 by r square, where k is a positive constant of proportionality and it's called electrostatic force constant. What is that one? Electrostatic force constant or Coulomb constant. K is what? Electrostatic constant or Coulomb constant. Let's see what is the value of K. In vacuum, the value of K is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. What is that one? Permittivity of free space. Let's see the same law in medium and vacuum, how it is working. Before that one, we want to know what is dielectric constant. Let's see the dielectric constant are the relative permittivity, the electric constant or the relative permittivity or specific inductive capacity or dielectric coefficient. What is that one? Dielectric coefficient is given as K equal to, can be written as epsilon r, can be equal to epsilon r, and epsilon r equal to epsilon by epsilon naught, epsilon by epsilon naught, epsilon by epsilon naught. For the medium, for the vacuum, what is this value? For the medium and for the vacuum. For the vacuum, it will be considered as 1 by 4 pi epsilon naught q1 q2 by r square. 1 by 4 pi epsilon naught q1 q2 by r square. For the medium, f equal to 1 by 4 pi epsilon naught. You take this one. Just epsilon equal to is what? Epsilon r epsilon naught. You can submit here. F equal to 1 by 4 pi epsilon naught epsilon r into q1 q2 by r square, where epsilon naught is 8.85 into 10 to the power of minus 12 Coulomb square per Newton meter square. Coulomb square per Newton meter square. So this is about the epsilon value, epsilon naught value. Then what is the value of 1 by 4 pi epsilon naught? So it will be approximately you can take this value. This is exact value. So most probably in problems we are using this formula, this value. 1 by 4 pi epsilon naught equal to 9 into 10 to the power of 9 Newton meter square per Coulomb square. Newton meter square per Coulomb square. Then Coulomb's law in vector form. In vector form, how you can consider the Coulomb formula. Let's see here. You are taking the vacuum and the condition is Q1 and Q2. The product of charges is greater than 0. Is greater than 0. Q1, Q2 is greater than 0. And from this figure, you can take from this side, that is about the toward the positive charge, F12 equal to the value of F at this particular point, that is at F12 will be considered as 1 by 4 pi epsilon naught Q1 Q2 by R square. Q1 Q2 by R square. What is distance? The distance with respect to F12, it can be considered as R12. It can be considered as R21. It can be considered as R21. But you are taking F12, so the distance will be R21. Similarly, with respect to F21, with respect to F21, and it will be considered F21 with respect to F21, and it will be considered as 1 by 4 pi epsilon naught Q1 Q2 by R square with respect to R12 distance, with respect to R12 distance. This is about the condition is Q1 Q2 is greater than 0. Then in case 2, if Q1 and Q2 is less than to 0, the product of two charges, if it is less than to 0, then what is the value of the force? That means you can consider here based on this F12 concept at this particular point, F12 equal to 1 by 4 pi epsilon naught Q1 Q2 by R square with what distance? The distance is, this is 1 2, that means 2 1. You can take as F12 and it will be F12, it will be F21, but you are taking that negative charge. So that is the reason F21 is changed into F12 to avoid the negative symbol. So that's the reason you're taking here R12 in the place of R21. We are taking R12 because to avoid the negative symbol. So similarly, F21 is 1 by 4 pi epsilon naught Q1 Q2 by R square. F21 R21. Generally here it should be R12, but the charge is what? Negative charge, so that's why it is rechanged, so it will be changed into R21. Now we can finally conclude that one. So F12 is equal to, see, F12. So F12, what is F12? 1 by 4 pi epsilon naught Q1 Q2 by R square R12. Similarly here 1 by 4 pi epsilon naught Q1 Q2 by R square, but distance here R12, here is what? R21. One is moving from charge 1 to charge 2, the distance we are taking. In the second case we are taking the charge, the distance from body 2 to body 1. So that's why they are in opposite character. This is about the vector formation. Similarly, and here this will be considered as, so here what is the unit of the charge? In SI method, the units of charge is called as the Coulomb. What is meant by Coulomb? 1 Coulomb of charge is that charge which, when placed at rest in a vacuum at a distance of 1 meter from an equal and similar stationary charge, repels it and is repelled by it with a force of 9 into 10 to the power of 9 Newton. That means what? You are taking that one, two different charges. This is charge 1 and charge 2. and these two charges, this based on the charge, this body must be repel certain distance. What is the certain distance? It must be repelled with the 1 meter distance. So whenever it is moving with a 1 meter distance, there has to be a certain force has to be applied, and that certain force is 9 into 10 to the power of 9. So if the force is 9 into 10 to the power of 9, if the displacement is 1 meter, then this will be called as 1 coulomb. In CGS, the value is considered as ESU, electrostatic unit. It will be what? Electrostatic, ESU. Let's see another one, the last one, which is the charge distribution, continuous charge distribution. Any charge any charge which covers a space with dimensions much less than its distance away from the observation point can be considered a point charge. What is the point charge? A point charge is defined as any charge which covers a space, any charge which covers a space. So you are taking a charge and the charges cover a space and with a certain distance, and that will be called as the point charge. A system of closely spaced charge is said to be a system of closely spaced charge is said to form a continuous charge distribution. What is that one? A continuous charge distribution. A system of closely spaced charges is said to form a continuous charge distribution. It is useful to consider the density of a charge distribution as we do for density of solid, liquid, gas. Density of solid, liquid, gas. Let's see the charge density or the continuous charge character will be three types. Let's see, the first one is line or linear charge density, and it's going to be represented by symbol lambda. If the charge is distributed over a straight line or over the circumference of a circle or over the edge of a cuboid, etc., then the distribution is called linear charge distribution. Here what is happening? The charge is distributed either in straight line, either in circumference, either in edge of cuboid, then this will be called as the linear or line charge density. It is represented by symbol lambda. Linear charge density is the charge per unit length. We have another one. Linear charge density is the charge per unit length. This is another definition. Then SI method, it can be represented as Coulomb per meter, then lambda equal to Q by L. Lambda equal to what? Q by L. For a small charge, for a small length, it can be considered as lambda equal to dq by dl. You can see the figure. From the figure, we can consider for the small length, it will be dq by dl. Coming to the second one, surface charge density, which is represented by sigma. If the charge is distributed over a surface, area, then the distribution is said to be surface charge density. Surface charge density is the charge per unit area. We have another definition. Surface charge density is the charge per unit area. The SI units is Coulomb per meter square. Therefore, sigma equal to Q by S, where Q is the charge, S is the surface area. Then you can consider for small charge from the small surface, it will be sigma equal to dq by ds from the figure. Coming to the last one, volume charge density, which is going to be represented by symbol rho. If the charge is distributed over a volume, then the distribution is called over the volume. Surface means surface distribution. Here you are taking, if the charge is distributed over a volume, then the distribution is called volume charge distribution. Then volume charge distribution or volume charge density is the charge per unit volume, and the units are Coulomb per meter cube. Then rho equal to q by r. For a small change, rho equal to dq by, sorry, here you can take the value is v, or you can take tau. Okay, anything you can take. I'm taking here v. So here for a small chain, q by v, and for the small, sorry, rho equal to q by v. For a small chain, it is rho equal to dq by dv. This is about the, so value means rho equal to q by v, surface means sigma equal to q by s, and linear means lambda equal to q by l. This is about the charge distribution. Thank you.